Hello, this video will provide a basic overview of the arm-lever equation and is presented by OSHAcademy Safety and Health Training. To help learn about the arm-lever equation, we're going to look at an example where a man is picking up a heavy box. In this example, the box has a weight of 50 pounds. And as we talk about the weight of the object, it's important to remember that weight is really a measure of gravitational force. So as we're talking through this example, remember that we're really talking all about forces. Even though we're describing something using weight, such as pounds, we're really thinking about this in terms of force. When someone picks up an object, or in this case a box, the object itself is always going to be some distance from the body. Now, even though the load or force of this object is only 50 pounds, the actual force exerted on the body is often much greater than the weight itself. The reason that the force applied to the body is greater than the force of the object itself is because the force is being applied across a point of rotation. In this case, it's the shoulder. The shoulder is acting as what we call a fulcrum, and this fulcrum amplifies the forces applied or felt by the body. This increase in force is what causes a lot of ergonomic injuries to the sacrum and lumbar region of the lower back. Now, the arm-lever equation allows us to model these different scenarios and understand exactly what forces are actually being applied to the body when we're lifting an object, especially when we lift that object a certain distance from the body. So let's take a closer look at this scenario to better understand how the arm-lever equation works and what forces are actually involved. We've already defined the load, which is 50 pounds, and the fulcrum, which is in the shoulder. The effort location is where we want to measure the forces actually being applied to the body. We label this location with the letter E. The distance between the effort location and the fulcrum is what we call the effort distance, and we label this DE. In our example, we're going to say the effort distance is equal to 2 inches, and this is a reasonable approximation for someone who's picking up an object and leaning forward slightly. The next distance is called the load distance, and we label this DL. This is the distance from the fulcrum to the load. In our example, we're defining this as 23 inches. And this is a reasonable approximation, as if you were picking up an object and your arms were stretched out in front of you. Now that we've defined the effort distance and the load distance, we can calculate the amount of force that would be applied to the lower back of our fictional character here. Now we can use a diagram to help us set up our arm-lever equation as we model this specific scenario. In our diagram, the triangle represents the fulcrum, and the two down arrows represent both the effort force and the load force. You might wonder why both arrows are pointing downward. If you think about it, gravity is pushing downward on both our character and the object itself, so the forces being applied are both pointing downward. The space between the effort and the fulcrum is going to be represented by DE, and the space between the fulcrum and the load is going to be represented by DL. We can substitute in some values now, 2 inches for the DE and 23 inches for the DL. And remember, the load itself is 50 pounds. The arm-lever equation can be written as effort times effort distance equals load times load distance. Using the values from our diagram, we can substitute in 2 inches for the effort distance, 50 pounds for the load, and 23 inches for the load distance. The next step is to multiply 50 pounds by 23 inches. This gives us 1,150 pound-inches on the right side of the equation. To get the effort by itself on the left side of the equation, we need to divide both sides of the equation by 2 inches. When we simplify the equation, we end up with effort by itself on the left equals 1,150 pounds divided by 2. After simplifying the fraction on the right side of the equation, we end up with effort equals 575 pounds. Now that we've solved the equation, what exactly does it mean? Well, what this means is that if we pick up an object 23 inches from our body that weighs 50 pounds, the force applied to our body is equal to 575 pounds. That's a whole lot more than 50 pounds. Now, from our reading, we know that anything over 550 pounds increases our risk of injury by up to 4 times. This type of scenario represents a real workplace hazard, and this doesn't even take into account the potential for twisting and turning, which would further increase the risk of injury. Now let's take a look at another scenario where instead of holding the box out at 23 inches from the body, we hold the box out at only 13 inches from the body. How is this going to affect the amount of force applied on the body? Will bringing the box closer to the body reduce or increase the amount of force felt at the effort location? Let's take a look. As we did in the previous example, we can set up a diagram. The effort distance is still 2 inches. The load is still 50 pounds. The load distance now is 13 inches. Using this information, we can set up the arm lever equation. As we did in the previous example, we can substitute in 2 inches for the effort distance and 50 pounds for the load. In this example though, the load distance is now 13 inches. Our goal is still to get the effort all by itself on the left side of the equation. So to do this, we're going to divide both sides of the equation by 2 inches. And when we do this and simplify the problem, we end up with effort equals 325 pounds. What does all this mean? Well, by bringing that object in closer to the body, from 23 inches to 13 inches, we were able to reduce the amount of force felt on the lower part of the back by 250 pounds. Now, this doesn't mean there isn't still the potential for a back injury. After all, there's still 325 pounds of force being applied to the lower back. But by using the arm lever equation, we were able to clearly show that using proper lifting mechanics by keeping an object closer to the body was able to reduce the amount of force on the lower back by 250 pounds. So if you're a training manager or supervisor, and your job is to teach your employees proper lifting mechanics to prevent injury, by using the arm lever equation, you can clearly demonstrate how using proper lifting mechanics is going to reduce the amount of force on the body and potentially reduce the risk of injury.